I'd like to introduce you Michael Supper. Michael Supper is a adjunct professor here in our group, and he is one of the well-approved or most approved speaker at Fall School. So I think it's the third or fourth time.
Third time.
Third time. So when he's not at East Fall School, he is the CEO at Roboception. So, and therefore we will get a nice industrial talk from Michael, and with some impressions what is happening with the perception and so on in the real world out there when the research is going out and we have to achieve things. Okay, so thank you very much for being here, and now please start.
Yeah. Thank you so much for the introduction, Jan. So I'm going to be talking today about solving complex automation tasks with 3D perception, and also about the power of synthetic data in conjunction with that. So you will see later in the presentation why I'm doing a lot with synthetic data, because we have to talk about where the data comes from, especially in industrial application. It's not the research world, it's the industrial domain, so we have to be a bit more careful about the data, and it also may not be always available. There will be some part a little bit interactive with you, so I will wake you up for that, and then you can help me a little bit on figuring out where you get your data from, but that's in the middle of the talk. So after that, I guess you are approaching the lunch break then. Good. First of all, I give you a little bit of an introduction to the industrial domain. So in the industrial domain, most of the time, robots are used in a very, let's say, simple way. So you've seen a lot of talks today where they're doing the dishes, they're doing a lot of intelligent tasks, but in industry, most of the time they're doing pick and place, pick and drop, fixed position, little sensory input. And the reason for that is that you have to have a process running here. You have tight cycle times. You have to make sure that the production is running. You have no one there that can just there and push the glass a little bit to the left when it needs to be grasped. So you need to have a reliable production. And the people dealing with the robots in the factory, they are not robotics experts. They're regular workers, and they have to deal with scenarios that should not be too complex to fix. So it's not like that you can call your best friend to help you with the robot there. So here everything needs to be quick, it needs to work. So the standard industrial way is that you're using the robot as a moving machine, so to say. And this means that the production is not flexible. So it may be okay if you have like automotive production where there's not so many changes in the part or in the environment and you know everything ahead of time. But now we are coming to scenarios, especially in the situation where we have not enough labor and not enough workforce, that also other processes, more complex ones, need to be automated in order to have the production. So usually what you have in a production, you have really no flexibility so far regarding workpiece quantity or even variations of the workpiece. So you're doing one part, and next time you're doing another part, but there's no changeover and no switch. Nowadays, if you have like specialized production, you have items that are way more changing as opposed to the classical production. You don't have really the skilled personnel unless you're doing this for maintenance and quality. That could be something that you have. And then usually you do precise feeding. So what you do is you're solving what the sensor usually does in the service robotics domain by metal. So you have mechanical feedings, you have everything fixed to the part and so on. And this means you're building a machine that can handle one part but not another one. And in order to go for more flexible production, there's a high need to bring basically these scenarios, which you can see up there to the left. So robot moves parts in dedicated places. Parts are more scattered or parts are even mixed in order to go for a more efficient production. So why is this a problem that you solve things with fixtures and so on? Because what you have to do is you're getting some parts that are in an unordered state, you get them to your production, and then there's two ways how you can get them ordered. and put into the machines. One is you do this by human labor. So basically there's a person that picks it and puts it in the right position, and then the process is solved. The more flexibility you have, the more people you need for that. Or you do programming, so you have an expert automation engineer, and this guy solves the task then by a mechanical fixture, by programming specifically, and so on. And then you have the work pieces in the order where you want them, and then you can continue with your production process. The problem is, and this is one of the reasons why robots and automation are a cost factor, this part here is really costly. Either it's someone doing the job, or it's a person that has to program it specifically. So any kind of automation, it's 30% of the components, and 30 to 60% is the automation engineering around it. And you can imagine if you make a cost estimate for what your production will be, this is a huge part. And this huge part needs to be smaller and smaller in order to allow for production and automation. And this is basically, when I was a bit younger, people always told me no sensor is a good sensor because a sensor can always fail and we need to do everything in a fixed way and then everything works. So this is a concept still in many projection facilities, and now you have to tell the people, hey, if you use perception, then this enables you to be flexible, because perception basically gives the position of a part. I'm only talking mostly about pose estimation today because it's still the crucial thing in production. How do we get the pose of a part and move it in an accurate target position? And you have to think the process always from the end, because it doesn't matter where the part comes from, it's always only relevant where the part goes to. So you have to tell people where does it go, and then you can decide how you pick it up and how you do the first thing. So think the process from the end. Yeah, I'm talking a little bit about 3 domains today, because these are the ones that are in the biggest need of automation today. So we have the domain of industrial automation, where you talk about accurate placement. So you have to put parts into machines, they are being milled, they are being processed, and then they have to be in a fixture, automatically processed, moved on. So that's what the robot has to do. But you mostly, most of the time, know the parts. So you have some information on that, what you're processing. In logistics, it's about unknown parts. And mostly it's about pick and drop, maybe pick and place for palletizing. But in most of cases, you have a large variety of parts that have to be handled. And many of them you don't know ahead of time, because it can be anything that's in the bin, that's in the box. And then, most recently, lab automation is a bit of best of both worlds from the two. It still has a challenging environment, so you have transparent parts, you have parts that are usually difficult to detect, but you have clear processes. So for me, lab automation is the automation step in between classical industrial automation via service to service robotics, because you can see in industrial automation, you know more structure about your environment. In logistics, you have a large variety of parts. In lab automation, you have the process and the transparency, and what you learn from these kind of domains can also be then transported to service, where you have no knowledge about the environment, a large variety of parts, and so on. So this is why from the industrial domain, we are going over the different verticals, so to say, towards service robotics to allow for automation there in a robust way. Giving you some examples here. So industrial automation, classical approach, I mentioned that already. You have mechanical fixtures, so that is metal that brings the parts in right positions. You have a lot of individual engineering for feeding and grasping. It's all done for this one machine. You have not more than 100 different parts, and you know them. So usually you have CAD data, you have data available from these parts. And it's always pick and place. So there's hardly any other operation that you have to fulfill in that domain. The vision system here can basically remove the fixture. So you have a more flexible cell design. In terms of cost, you always compare fixture versus vision system. So the fixture is like 10K. The vision system should also be 10K. So this is very easy calculation, but this is what you compete with when you want to do and bring some sensor technology in a production. You have to compare the existing cost towards the new cost. The model-driven approaches you can use here because you have model data available. It's not unknown objects, it's known objects. And you can combine the approaches, machine learning and classical algorithms, so it's both possible in this case. In logistics, you have very high cycle time. So usually around 1,000 picks per hour. That's usually what the human does, so to say, when you're picking parts from left to right and dropping in somewhere. You have a lot of parts. All of them are different. You don't know what's coming. That can be small bags. It can be larger bags. It can be any kind of item. They are unknown, and it's mostly pick and drop. So you take from one bin and drop it to another to commission the order for the end customer. Here, the vision system actually is the key enabler for robots, because without vision, you don't fulfill the task. So in classical automation, you could work without sensors, but you're not flexible. In logistics, you need sensors because you don't know what's coming. So this is why the driving force for sensors in robotics is actually logistics, because they need to have sensors. Otherwise, they cannot automate these tasks. Here, mostly data-driven, because you have basically unknown parts, so you have to learn from what you see. And yeah, if you can do a shared approach here, you know a little bit and you know a little bit over time. Some logistics providers, they have a little bit of a model database of the products they have, especially like discounters. They actually have less products, so they know a little more about what they have in the stores. But if you come to a large wholesale, then usually that is not the case. And then lab automation, so you have a traceability of the process. You have transparent objects most of the time. And it's also pick and place, because that's what people are doing, usually bringing parts from A to B. And here, basically, the application of a mobile robot with a sensor makes a lot of sense, because the qualified personnel that you have in the lab, it's actually a lot of waste of time for them to run around and pick and drop stuff. So they should be focusing on the process they are working on. And this is why we see here a lot of automation recently. Mostly mobile robots, very simple grippers, simple system. I mean, you've seen the Ubica system yesterday, so imagine that with a very simple arm, and that's one of the systems that you see in the lab automation domain. Good. This is just a video from one of the production sites that we are in, so I can share this with you. So this is how it actually looks like, right? You have here some inbound parts. You have a robot here that has a target thing where the places are part. You have to pick them up from various inbounds, right? Some of them are coming in paper pallets. Some of them are having other trays. There's usually someone loading that into these docks. And then you have to figure out where the parts actually are, and then you have to put them in the next processing step. You can see that light is usually a problem, so and it's actually not as clean as you would understand in production to look like. So there's a lot of parts. Of course, always you have sunlight from the top, because usually there's windows in the ceiling, so to say, and you have no environment that you can really close from external light, right? Big problem for the vision. Here we have a system that's a robot on a rail. We have cameras on rails. And this is basically a system that was refurbished, so to say. It used to be a different setup without the external vision system in order to improve the performance. So this is actually a system that is like 15 years old. And after 15 years, people start thinking, what can we do new in our process? And then you have to live with some constraints they put in the past. So you're not starting a new cell, but they come, okay, these gates are all fixed because this is a place you have, and then you have to see how you can make something better in that domain by introducing 3D vision, which we did. Again, to the end of the presentation, you will see basically the improvements that we made by 3D vision, but just giving you a little bit of an insight on how these kind of scenarios look like. Good. What is the challenges, especially from the 3D projection side? So you have a lot of variables. So you have a variation in the environment. So basically, there's changes in illumination, changes in point of view. So you don't have always the possibility to see the part as good as you want to see it, because there are some constraints. The robot needs to have some space to reach the part. So if you have consider the situation we had before, these pallets are up to 2 meters high. So, and then now you just have to decide for the right viewpoint for the camera to see the top layer and the bottom layer, and in between there's a robot moving in and out. So this is a constraint. So you have to cover a range of 2 meters approx, and you're 1 meter above. So in this case, 3 meters is the maximum distance from camera to the bottom of the pallet, just by the physical constraints that you have in the scene. So, and it needs to work for the top one and also for all the lower ones. So they don't care if it's difficult or not. They just want to know that it always works and you empty the pallet. And then illumination. So in this application, it runs 24/7. So it's installed in Denmark. So it's pretty bright in summer, pretty dark in winter, and 24/7. So this is basically the illumination that we see during the day. You have a variation of the object. In this particular cell, we have covers, we have dark black coils, and we have shiny metal parts. So that's the 3 parts that it's usually, they are building frequency converters. So all the parts, they are very different in nature, have to be treated with the same camera in the same environment. So you have changes of material, and you have various sizes. So the coils are like that, and the covers are like that. But all they have to be treated from the same distance and then in the same accuracy, so to say. And then you have a variation in the application. So usually the parameterization of a production requires expertise. And the question is, do you have that? Is there someone there who has the expertise to check on a dashboard, this is parameter A, B, C. So best case, you don't have any parameters for the people on the shop floor, because if you have them, they try them out. If they don't know what they're doing, they're stopping the production. So basically, do everything in a very simple and limited way. And you as a developer has to make sure that the application people do the right thing. So it's not like, as a developer, you like to have many parameters because you want to try out things, and then you know what you're doing, and then you have your perfect set. But then there's this other guy who's using your machine, and he doesn't care about any of your parameters that you needed in the development. So there needs to be a different interface to the system for the person using it and the person developing it. And then it's all about testing and commissioning. So when you have this installation, usually it takes a month. You go to the factory, you have to run through acceptance tests, so the machine is running, the customer checks for every error that happens, they are listed down. Next time you have a couple of weeks to improve that, and at some point it's then running in production because they have a certain KPIs that you need to fulfill. So, and this is also something you need to consider ahead of time. Especially the last point here is risk, right? So you're going into an application, it goes to the customer, and on the customer side you figure out that you have a problem. So that's the worst situation where it can happen, because on the one hand the customer sees it, and secondly this is actually cost, because maybe globally somewhere else you have to go there, someone has to check it, so you're losing all the money that you wanted to earn with this project just because of that. So this is basically the reality that we are seeing there. And the question is, how can we make sure that we are reducing the risk here? So we want to know as early in the process as possible what are the things that we need to look at. And this is what you need data for. So you need data for this particular project that you're running, which will be installed later on, half a year later, a year later, and you need to know how this works. With real data, this is difficult, because you cannot just go there and say, hey, I'm recording here 24/7, and then I take all the data home. Usually they don't allow for that. Also, you don't know which scenarios you have to record at that point, and it's a lot of time. So this is why we usually take different approaches in these kind of scenarios. Okay. I said most of the time what we are doing is post-estimation. So Roboception does all kinds of applications, but in the end it's post-estimation. So you could call us also a post-estimation company. Of course we sell it differently, but technically it's post-estimation. So the question is, what do we do? Usually we do a two-step approach here. So we have a bounding box detector, maybe RetainerNet. We're doing some pre-trained classification or segmentation for unmixed. So there's a different way how you can do this first step. Second step is usually a post-prior estimator. using autoencoders, different things, so bounding box, post, prior, or classical methods. So some applications, they don't have machine learning at all, depends a little on the case, if we have training data or not, but basically that's the same way. So usually you do your bounding box and you do your post prior, and then for pick and place operations, you always do a post refinement. So there's nowadays a lot of neural networks that do everything in one. But in terms of like the development of a scalable software pipeline, it makes a lot of sense actually to split it in these 3 steps, because depending on what is happening on the shop floor, you may want to change just one of them and you don't want to retrain all. So basically, this is why usually you recommend to have this kind of variable flexible pipeline, because sometimes you don't need a bounding box, you just need a post prior. Sometimes you don't need the refinement, and then you can basically reuse your experience that you have for other applications. For pick and place, post refinement is necessary because you want to be accurate to sub-millimeter in order to grasp the part correctly. For pick and drop, usually post refinement is not necessary, so you can skip that part. We are using most of the time for the bounding boxes RetinaNet at this point of time. Of course, there's multiple other application or nets you can use for that. RetinaNet is all but good, so to say. There's a lot of new stuff that you can think of, but it gives you a good indication of what this first step actually does. So you have a batch of RGB images, any size. You're getting some bounding boxes and scores out of that. In practice, you have a resolution and a couple of parameters, like 4 parameters for the axis-aligned bounding boxes and 5 for object-oriented bounding boxes, and that's basically the first step that you run with your bounding box detector. You can do it single stage or 2 stage. I mentioned that already. 2 stage would be you're creating a sparse set of bounding box candidate, and in the second stage you classify them into foreground, background, and the single stage is that you look at more candidates, dense, and completely fill the image. So the candidates that you're getting, you're usually calling anchors, and the dense anchors are actually a problem for the classification because of the imbalanced data set. So you have much more background and foreground. And I will show you some details, especially when it comes to bin picking, and you have multiple objects of the same kind on top of each other. This may result in some problems here. The anchors are usually as such. So you have this anchor boxes in your input image. You create a feature map from the subnet, and then you get your representation, the quick reference down there as well. So far, I guess most of you have worked with any bounding box detector so far, giving you just an insight here how the process works. And then the interesting thing is oriented bounding boxes or axis aligned. So giving you some examples here. You can see that from left to right. So this is the scenario that we are having. And here you have the issue with the axis aligned bounding boxes, because these are the scenarios that we see most of the time. So objects are never separated. If they come from the bin or from the stack, they usually do overlap. And then, of course, it helps a lot to have an axis-aligned bounding box here and work with that. Also, there are some issues that objects are very long, especially when they come from the bin. So usually people say, you know, there's a stick in a bin, that's a simple part that's easy to grasp. But if you deal with a bounding box detector, it's really bad, because it may span a large area of the image, and you have so many items in that. So the customer says, hey, this is the most simple part I have, and you're telling him, hey, with my bounding box detector, that's actually a problem, and then they don't understand why the simple part may have issues with the bounding box detector. So because they don't understand, hey, they look at a simple part, you should be able to pick it, no worries, right? So this is why most of the time the simple parts are the problematic ones, because they don't have enough features, they're pretty roundish, and so on. So the customer says it looks simple, for grasping it's bad. If you come with complex cases, they're very happy. So whenever they come with testing us, they usually send us a complex part, it's easy for us. But then they say, oh, no, I have this very simple one. It's just a cylinder. How can you do this properly, that it's graphs always in the middle? And then you're like, okay, this is actually the more problematic case now for us. But yeah, that's how it usually goes. This is why carefully think about your scenario, what kind of bounding boxes you use. And usually we would recommend to go for the object-oriented one. It's a little bit of more effort, but it's definitely worth, especially for these unstructured environments when you don't know how the parts are coming. Okay, of course we always look a lot into benchmarks. This is the one you probably know, the BOP benchmark, the most relevant one for pose estimation, and even coming from the industry side, that is what we look at, because you see a lot of new applications happening there, new approaches coming there. They may not have like industry relevant parts, but for us it's good to see which methods perform well. In the end, we are dealing with systems that have a computation time of 1 to maximally 3 seconds. This also means that many of the approaches are basically off topic for us, because computation-wise, I don't think there's any system that allows you for more than 3 seconds for pose estimate. This is why usually we have to check on the runtime and the complexity of the algorithm. And lastly, I mean, in your research labs, you may use the biggest GPU possible. But if you deploy this to production, usually that's not possible, right? So there's some constraints, or what kind of material can be into production. There's only a few graphics cards that are allowed to run in production, because especially in the US, there's a thing that's called NRTLUL, which means that you make sure that the devices don't burst into fire, and then you need to have certified devices that work on that, usually in the US. So this means you have a very limited set of graphics cards that you can actually use in your production. So all the things that you do in your lab may never come to production if you need more than, I don't know, 60 gigabytes of GPU RAM or something like this. So you have to basically break it down to bring it there. So this is also an important thing to know. And it needs to work in industrial environments up to 50 degrees Celsius, protection classes, and so on. This is really constraints. And this is, the benchmark is nice, and then you check on the runtime, and then mostly on the resources needed. And this is basically which selects that you usually don't take the best method, but the one that has a good trade-off between performance and data. Okay, now we come to a short interactive session, because I know it's shortly before lunch, and I just want to gather with you together some information on what you actually think about data and where you get it from. So I have prepared 3 questions for you. We will do a quick Slido. You can do this with your phone, and then we just want to figure out what kind of status on data we have here. So there's 3 questions. Synthetic training data, it's about the data that you have available. Unknown objects, you need to label the data. How are you doing this? Are you doing this in a certain way? And then last question would be, which are the data sets that you use for training, if you use any? I will click to the next slide, and I hope it's opening up. So that's the Slido link. You can do this from your phone. And in the next, we can see live the question. So basically, for the unknown object, real data is required to the synthetic data. Where do you get your labeled data from in this case? I labeled myself. I use labeled data from known origin. I use labeled data, but I don't know where it comes from. I mean, some people just do. Right? And I've never worked with labeled data. So I think that should cover all of you. And yeah, I think we're around 5, 6, 10, 30 people here, 40. So let's see, if we reach 30 up there, then I think most of you participated. Okay. That is interesting. So you label, most of you label yourself. And what's your experience with that if you label yourself? do you know enough to do this in a proper way? Or do you have students doing this for you? Or, I mean, that's time consuming, right? The question would be, why are you labeling yourself? Yeah?
Mostly because we have very special use case where there is no big data set already
Mm-hmm.
from somewhere.
Mm-hmm.
So like special cases with special data which you
Okay.
basically don't have a source.
So you basically get the data, you label yourself because you don't have the right data set available. So that speaks a lot for more relevant data sets, I would say. Or are the cases very special?
I guess they were special because I think most of sophisticated data sets are like for perception for like images,
Mhm.
images,
Mm-hmm.
and I do like much like force control data.
Okay. Okay. Good. Okay. So yeah, most of you then either label yourself or know where they get the data from. So it's also a matter of trust. Okay. Good. Sounds good. Let's move to the next question. If you work with synthetic data, this is usually something you have to consider how your data is correct, not correct, or so on, and if you know if it's correct or not. So you need to have model data, you bring it into your Blender pipeline whatsoever. So the next question would be, is the data usually available but not exact? Is it exact? Is the data available but you don't know if it actually fits? Or you don't have even the data. So it's also interesting to see. It's a self-assessment, right? So we are not checking if it's actually true. So okay. So there's a majority of data available but not exact. Oh no. Kind of. Okay, good. So most of you have data, and it's a short or small difference between exact or not exact. One question to that, do you know what is not exact in them? Because that was hard for Slido to do. So you know the problems in the data?
I think most of the time you have CAD models, but not the appearance.
Mm-hmm.
I like exact
Right.
materials, and especially if you're working with metal parts, sometimes they're a bit rusty if they're used or so, and
Mm-hmm.
this is very hard to model.
Yeah. What do you then do then?
Sometimes we apply like patterns to the surface,
Uh-huh.
but yeah, they're still not the exact reality.
Yeah.
obviously.
Okay. Yeah.
And yeah, it's also a lot with like different lighting conditions that you can play
Mhm.
around, but yeah.
Mm-hmm. Okay. Usually we ask for pictures on top. So basically we get the CAD model and ask the customer for a picture of how the parts look like in order to assess that. That's exactly the same problem, that you don't know the material and then you don't know the true appearance of the part. Mm-hmm. Good. Okay, good. Last questions. This is a free-from question. So what are the data set you're usually using for training? So some of you said you're creating data sets yourself because you're labeling yourself, but is there something that's maybe in this area here, the predominant data set? Maybe we can find something like that. Mm-hmm. Okay. Okay. For pose estimation. Yeah. Okay. It's not summarizing them properly. Okay. Uh-huh. So would you like to have more data sets? Because that's really a question to have, because if you're doing your own data set and you're training on that and you're working on that, how do you compare, right? You can make it public, but I mean the tasks that we have to fulfill most of the time, pick and place, some domain, pick and drop, some domain. I think it would make a lot of sense to have pick and place for, let's say, this kind of task, a data set that people can work with and benchmark with. Because then it's not individual work, because the question is always, are you labeling correctly? Are you doing this all? And you have your data set, it works fine for your application, but the next person starts all over again. And for robotics, I think we need to have like a secure task execution, and this is why I think that's very important to have data sets for tasks, so to say, and that contain the data, and not only vision data, but also like, let's say, robot data and all the other stuff, because we are not, as a vision guys, not freely decoupled from the rest of the world, so to say. So this is kind of important. This is why I asked this question. You have a question back there? Yeah.
So for the JCP, for example, the good thing about this data set is that we also have the objects at our university.
Mm-hmm.
This is also used within Robocop, for example. And
Yeah.
other teams have them as well, so training is much more easy for every team, and you can compare the robot quite good.
Yeah.
So having like more data sets online that you also can buy as physical objects, that would be nice.
Mm-hmm. Yeah. That's true. I mean, that's the good thing about that, to have real object with this that you can test also in reality. But this also comes at a complexity if you want this globally, so you need to make sure that you're getting these parts globally in order to do this. Yeah. Yeah, that's the other problem that's behind. What about the real parts in the back end? If you don't want to do everything in simulation. Okay. Good. Yeah, thanks for participating. I hope you're all awake again. And now I'd like to give you a few insights on the synthetic data that we are using for our application. And basically, I see 3 trends at the moment. One is that in robotics, we are not talking so much about big data, but good data. So that's relevant for our application. It's not like autonomous driving, where there's huge data sets available. For manipulation, you usually have smaller ones. Second is you need to make sure that you implement this in a scalable platform that people can use. And last but not least is the end user is dealing with a complex system, and machine learning can really help to reduce the amount of parameters that the end customer sees on the screen, because you're doing this in the training already. So this is machine learning is also a usability feature. Because it reduces the amount of parameters as opposed to classical approaches. And this is what I'd like to be focusing on in the second part of the presentation, on the good data and also on the usability of the solution. Okay, so this is an example here. So for a pick-and-place application, all of you know this kind of part. It's in most cars, and you hopefully use it. Basically, for this kind of application, we have some specifics of the part, and the task is you have to pick it from bin, and you have to bring it in an end state with a grasp point positioned on the part, and then basically do the application. We are doing this in a simulation environment, so basically we are picking up the part, and then we are basically bringing it in a photorealistic simulation environment with a material library, so we can change it from metal to plastic and so on. And this basically allows us to do a training without real data recording, which we usually don't have from the site. We can support different use cases, stacked scenarios, different scenarios when the customer knows the parts are coming in an order, basically stacked on intermediate layer or fully chaotic, and it can also be used for multi-material. If you look at this, basically, this synthetic data saves you a lot of time because you can check if you can do a detection and you know the true pose of the part. The problem with the labeling is usually that you need to make sure that you're getting it correct, and you don't even know the correct pose. In a synthetic data set, you always know where the part is in the true part, and you can benchmark it against the ground truth data. In order to do this, you can estimate the achievable detection accuracy, because you know where the part is in simulation. You do the detection, you see how close you can be in millimeters and degrees. You can compute the point cloud, and you can even enrich the data with real data, because it's just images from synthetic environment, and you can mix them with real ones if you have them. So you have a quite powerful approach to even feed in real data. And then you need maybe 3 to 4 real pictures, but a lot of synthetic pictures. So that's really a good combination in order to also reduce the true parts. Yeah. How do we do this? So basically, we usually get the CAD model. We ask for a picture of the part just to see how the material really looks like, and then some application description. So usually people know you pick it from a bin, and all parts are next to each other, nicely stacked, or you pick it from a bin, fully unordered, and so on. And then usually we also ask the customer, what is your expected working range? So where can we put the camera and how far it is away, so that we can have a nice simulation here. And with that data, we are doing the training, and we are generating basically a template that is used for the detection, has no parameters, and the report that gives us accuracy estimates, basically all the execution, do we have flips in the data, and so on. So we get that all from the simulation, and based on that, we usually judge if we can do the case or not. So it's very simple in the early stage. So you say, this is the accuracy you can reach, and then we can say, hey, customer wants a micron. We say it's 2 centimeters. Okay, we will not have a deal here. So basically, we can judge quite early in the process before seeing the real part if this is a feasible project or what the project risk is. And that's very important. We can optimize with real data, and what we usually have is like 300 simulated images and 1 to 5 real ones. So that's also from the data set size still okay. And it is based on the CAD model, so we don't have any data protection issues or any like that, because it's generated from CAD. How does it help us? It's in robustness, so we can cover all variations in the environment, in the object, in the application. We can validate against ground truth, and we can change the lighting and the material. So we can do all these things that you can't do in real, turning off the light, opening whatever. That is something what we can do. We just need the CAD, some basic information, how the task looks like, and we don't disturb our customer in terms of downtime, because we have to go there, see for things, and so on. And we don't need any expert knowledge to parameterize, because we get a template and it's basically upload and detect. So that's quite easy for anyone. Effort and cost, an important thing. We can do the feasibility of the task already in simulation ahead of time. And the commissioning on-site is much easier, because you don't have to adapt so much on-site with parameters and so on. And we can do efficient remote support. We are a company based in Munich, but we have customers globally with that, because we can do this most of the time remotely. So we get snapshots and then we can move back. So we don't need to go anywhere. So I think in 8 years we have been at 2 customers from the 100 customers that we have. So it can be done remotely if you do it in such a structure, which is really helpful also for people not needing to travel everywhere. The use cases, so this basically is the part that you've seen already in the beginning. So the important thing about that part is that it has this small little ditch here. That's a so-called Poka-yoke thing, and that makes sure that the worker puts it in the right orientation into the machine. So it has no function, not a function for the part, a function for the worker, so that we can make sure that they put it in the right way. So there's a lot of these things in industry, Poka-yoke, to make sure that people don't make mistakes, and this is one of them. And the question is now, what does it mean for us if we do a post-estimation task? So basically, this is one of these reports that I mentioned before. So we have a couple of information on the sensory distances, how far the part can be away. And then it's the question, what is the working range? Where do you place the camera? So we have a couple of sensors here available. They all have different working ranges. We need to make sure that we see all the parts. We need to see at least 80 pixels of the part. And we have basically a minimum and maximum distance that comes from the application. And based on that, we can decide for the sensor that actually does it. From the report, from the best match parts, you can see something here which is a little bit, basically bad in that case, because the position accuracy in millimeters is okay for the customers, but the rotation accuracy here is very low. So you have a variation of 38 degrees in the mean, 72 degrees in this in the orientation. Why does it happen? Because we considered for the pose estimate this area here. So in this case, we said it's important to see if this part is oriented in the right way when you take it from the bin. And of course, this is a small feature, and you can imagine they are all stacked like this in the bin. It's really difficult to see this small little thing and get it in the right orientation. In this case, the solution was to say, hey, we are ignoring this special feature, and we do a singulation first and then a pose estimation accurately in the second stage. That is also what you usually have. If you want to solve this in one step, this production will never work because you have so many errors, the parts are not well detected, and you don't get them out of the bin. So in this case, the solution was to say, we put it in 2 steps. So we get it out of the bin, and then we check if the orientation like this or like that, and then we flip it, and then it's it. So basically, that's also always possible, and that's one of the decisions you have to take early in the process, because this flipping station doesn't need some space, needs to come from somewhere. You have to discuss with the customer regarding cycle time and so on. So this is why the simulation is very helpful, because we saw in the first half hour what the problem in this case is without even having tested the case. Okay, I have to go back here. Then we can run it all in simulation, run the data as real images, so to say, in a simulation mode on the camera, show it to the customer. So basically, it's also nice. We can download images from the real system. We can upload virtual images in the camera. So basically, we can do both to test and figure things out. And then we basically have these scenarios with the object detection where we have the individual parts placed inside the bin and can run our synthetic simulation to do all that, what we need to do for this application. Good. We use this also in a couple of different places here, giving you some results from European projects. So this is a white goods case, so to say. This is cooktops, so the ones that you have in your oven, the ones that are on top. They are black on black, which is very nice. So you have a black metal part in a black tray, and you need to pick up the black metal parts. So you can imagine that this is kind of difficult. So in this case, we actually used some real images in order for adapting to that, because we couldn't really define this scenario also with this nice reflections in here in the real scenario. And then we have another scenario, which is in this, also from this pilot, which is about aerospace parts, where we have to use that clamps on the Fenkel, and they need to be detected in order so the robot to grasp the whole part correctly. And here we have also this scenario, black background, white part in front, and need to have a nice adaptation. So also there, the picture of the part helped to get the material straight, because as you said already, that the material information is not really always correct when you get it from the cut, or that you can really use it for your simulation. The question is now, how do I reduce the complexity for the customer? Because usually robot vision requires expertise. As a person on site, you don't have it. And the question is, how can we make it simple in this case? We have some scenario here. So I'm showing you one video that shows the graphical user interface. So you may need to make it accessible. So people want to see pictures. On pictures, they can decide easily how things work. This is, for example, a way how you can basically, you can select the exposure region. So the customer knows this is my bin, and then they're setting exposure in that area. So of course, you can do this in coordinates always, but people that don't know about coordinates, they need to see what they are doing and they know where their bin is. This is why they need a way to interact with the system in order to set the parameters right? So this is quite important, and this is a big advantage of systems if they offer easy access. So sometimes you would say, hey, that's not really needed, but people trust what they see. So if they can do it themselves, they can see the result quite easily. Everybody can, if they do a detection, you compare the images to each other, then you have a trust in the system because you see what the system is doing. And doing that in a nice, comfortable way, where you don't have too much parameters with these, let's say, tryout button, everybody is happy with the result, and especially the tryout helps us a lot to make things accessible for non-vision experts. Good. How does it work then when you have a complex automation project? So you figure out your application requires robot vision. You collect the information, as said already, so description, photos, specs, load carriers, 3D models, whatever you can deck. Usually we have a form for that, and people just fill out what they know. And what they don't know, they leave blank, and then we have to deal with that. So it's a very simple form that gives us a rough idea what they want to do. Then we do this basically feasibility recommendations. So if you're doing vision, you bring a solution in or a vision component in, but you have to check what's left or right. So you always need to see what the robot needs to do before and after in order to provide the right solution. So this is why you need to check on the use case always. So if you say, hey, the camera only has to do the pose estimation, maybe nice, but if you don't care what's before and after, you will not be successful. So you need to consult left and right on the application, on the gripper, and so on, because usually people say if they come from mechanical fixtures, sub-millimeter accuracy is no problem in grasping. Now try to do this with a camera. So sub-millimeter accuracy in the pose, I doubt that anyone of you would offer that. So you have to talk to the people that you may have to change something here, because I cannot give you microns, right? So you have to be a little bit tolerant on some parts. We get the cut model of the part, we do this analysis that I just described. If we have doubt about the case, we ask for some recordings or testing the parts in physical, and then we can run through the whole process. So that's a very nice way of going through an application project and ask all the relevant questions on the way. So that is basically the end of the presentation. So I'm closing the loop. I'm back in the same scenario that you've seen in the beginning. As I said, this was a retrofit of a cell, and we added 3 revisions. So we had 2 cameras on rails that were looking from the top, and now the cell produces 40% more parts, and especially because you have no downtime. Cycle time is usually clear, but if a system has downtime, it goes on the cycle time. So if you run every 10 seconds and then you have to stop the machine for half an hour, your cycle time is lost for the whole day because they compute it on the time. This is why you have to avoid downtime, and this is why, especially with the robust solution, you bring this to a reasonable level. So in this case, they have now the issue that all the machines afterwards have a problem because this one is producing 40% more. So now they have to start reworking the rest of the process because we are getting more parts out of this machine now. And this is then what's happening next, and this is how we get more cameras into that. But that's basically the way it usually works. Yeah, with that, coming to my last slide. So if you do vision in the field, you have to offer a more complete solution. So you have to check on your component, but also what's happening left and right. You need to be sure that the process works. It should be easy, and the implementation should be intuitive. You should use standardized interfaces to be interconnectable. Cost efficient is always an issue. Always saying that price is not the only one, because there's always someone that can do it cheaper. So if you are in the pillar complete and easy and versatile, cost is not the dominant one, but cost is a very risky factor, because as there's always someone doing it cheaper for it, then you can do it. And versatile, so you have to make it compatible with many systems. And the most important thing is, if you do vision in industry, then should be no vision expertise required from the end user. So because it's not available, they will not use a system where they need to have deep expertise in. And this is something that we need to provide in order to scale vision solutions in the field. So the most important thing. Good. That's the end of my presentation. I hope you enjoyed it, and I'm happy to answer your questions.